All right, what up, everybody? Today we're talking about kinematic equations, which are equations that we can use to find the motion of things. All right, we can find, depending on what equation we use, we can find velocity, either the starting velocity or the final velocity. We can also find acceleration, and we can find displacement as well. Okay, so here's a velocity graph, and a velocity graph is useful because it can tell us acceleration and displacement. Okay, and it can tell us pretty much the acceleration displacement in any circumstance, no matter how complicated the motion is, because the slope of the velocity graph is going to be acceleration, and the area under the graph is going to be displacement. So as long as you can find the slope and the area, you can always find the acceleration and displacement. Okay, but sometimes it's easier to use an equation because with an equation you don't have to draw the graph, right? So that saves time. So let me show you what equations we have to work with and how we get that information from the velocity graph in the first place. Okay, so first of all, if you want to find the acceleration from a velocity graph, what do? You find the slope, the rise of the line over the run of the line. Okay, so in this case, the line goes up 20, starts at 10 and goes to 30. So it up 20 and over 10 because it takes 10 seconds. So you divide those and you get 20 divided by 10. Okay, but let's think about what we're doing. Okay, what does 20 represent and what does a 10 represent? Okay, are they just random numbers or do they represent um, something physical? Well, if you look at it, the rise is 20 because it goes from 30 up to 10, right? So what we're really doing is we're taking the top value and subtracting the lower value. 30 minus 10 equals 20. The top value is just the velocity at the end of the time. Okay, we're only looking at 10 seconds of this motion, and at the end of those 10 seconds, the velocity is 30. Okay, we look at the numbers over here on the y-axis to find that. And the 10 is just the starting velocity at the beginning of the 10 seconds. So we're going to replace this 30 and 10 with Vf for final velocity and Vi for initial velocity. So the rise of this line is just Vf minus Vi, final velocity minus initial velocity. Okay. Now what about the run, the number on the bottom when we find the slope? Well, that's just how much time goes by. Okay, do you see that? Starts at 0 seconds, ends at 10 seconds. All right, so really what we're doing is we're taking the difference between the final and initial velocity and dividing it by the time. All right, so let's just replace numbers with letters. Okay, acceleration is equal to final velocity minus initial velocity divided by time. Now, is that always true? Yes, it is. Okay, it's always true as long as when we can't use this equation when the acceleration changes. Okay, but for a period of time where the acceleration remains constant, we can use this equation every time. Which means if we don't have the graph, right, and we don't want to draw a graph, and we know what VF, VI, and T are, we can find the acceleration. Okay, so here's that equation. All right, now it gets better. Okay, let's say we know the acceleration, but we want to find the final velocity, which seems to be maybe a question that we might ask more often. But we can take this equation and we can fix it. Okay, and this is the stuff that um, nerdy people daydream about. But here we're just taking this equation that we just found using the graph, and we're just using algebra to change it. Okay, and you probably don't have to know how to do this. I just want to show you that this is how we get this equation. Right, and so we take the t over to the left side, multiply both sides by t. Then we're going to add vi to both sides, and you get vf on a side by itself. So if you want to find the final velocity and you know everything else, then it's going to be acceleration multiplied by time plus the initial velocity. Okay. So there you go. If you need to write that down in your notebook, go ahead. And we're going to find another equation that can be useful to us. Okay, this time, let's look for displacement. And remember, displacement is the area under a velocity graph. Okay, so if we found the area under this graph, then we have a rectangle at the bottom, because it starts with some velocity, so we have to find the area of under that, and then we have a triangle on top of it. So we can split this shape up into a triangle and rectangle. Okay, the area of this rectangle is just 10 times 10, right? Because there's 10 seconds that go by, and there's 10 meters per second of velocity there. All right, so you just multiply those together to get the area of it. Then for this top triangle, the height is 20, the base is 10, so you just multiply the 10 and 20, but you have to divide by 2 because it's a triangle, not a rectangle. Then you add those two numbers together up here. All right, now let's again, just like we did with acceleration, ask yourself what these numbers mean. All right, I will start with the rectangle at the bottom. Obviously, the base of it is just the time that went by. But the height of it, notice the reason that there is this rectangle in the first place is that we have a starting velocity that's not 0. It's 10. Okay, so that 10 equals the initial velocity, right? Now, so the rectangle is really just the time multiplied by the initial velocity. Now, the top triangle, the height of it is equal to Vf minus Vi, just like we saw with the acceleration. It's the final velocity minus initial velocity. The base of the triangle is also equal to time. It's the 10 seconds that go by. And so if you multiply those two numbers together and divide by 2, you get the area of this triangle. Okay? So let's replace, and then you add them together. So let's replace the numbers with letters. This is the area of the rectangle. This is the area of the triangle. Okay? And to get the displacement, you have to add those two together. So instead of 10 plus 20, we're going to replace it with the letters. We get this equation right here. Okay, now is that equation useful to us? The answer is yes. Okay, because now if we know how fast something is when it started, we know how long it took, and we know the final velocity, okay, then we can actually put numbers in and we can find the displacement. Now, I should notice that this...
Staff, just a reminder, the Makeup Faculty meeting will be starting in 5 minutes. They're in the auditorium. Once again, the Makeup Faculty meeting will be starting in 5 minutes in the auditorium.
Okay, so notice that if you know these numbers, I mean, if you know all these variables, you can find displacement. This only works if there is a straight line for the slope of the velocity graph, okay? Because that's when there's a straight line, then you have triangles and rectangles, okay? If you have like a curved line or this changed slope, then you want to be able to use this method, okay? But we can take any period of time where the acceleration is constant, and this method will always work. Okay, this equation will always work. All right, but we're going to change this equation a little bit, and we're going to fix it in such a way using algebra that's going to be even more useful to us. Okay, so you recall this is the first equation is the equation we just found using the area, and the second equation is the equation we found for acceleration. All right, so we have Vf minus Vi here, and we have Vf minus Vi here, which means we can replace Vf minus Vi with a times t, acceleration times time. Okay, so that's what we're going to do. Okay. So now we have this equation, which you multiply the t's because they're like terms, and you get this equation. Displacement is equal to the initial velocity multiplied by time plus 1/2 acceleration time squared, right? Now, if the acceleration is constant for a given amount of time, then you can find the displacement during that time using this equation. You don't have to draw the graph. All right, so that's the benefit of these equations. Now, the drawback to the equations are that if the acceleration changes, you can't use the equation. You can still use the graphing method, right, and cut things up into more shapes and then find it that way, but you can't use the equations if the acceleration changes. Okay, so Next, what you're going to do in your class, here's the two equations. You're going to use these equations and you're going to answer a question, all right? How fast do things accelerate when they fall? So you can get into groups. Design an experiment to find the magnitude of acceleration, meaning how big is the number for acceleration for falling objects. Does this value change if you drop things from different heights? Does this value change if you drop things with different sizes? So the way you do this is you're going to use this equation where displacement is equal to the initial velocity multiplied by time plus 1/2 at squared. Okay, now how are you going to use this equation to find the acceleration? Well, displacement, if you drop something, all right, displacement is just the height that you dropped it from. Okay, also if you drop something, as long as you don't throw it, if you just drop it, then the VI, the initial velocity, is 0. Okay, which means this term cancels out completely. So if you can find the height that you dropped it and you know the time that it took to hit the ground, you can solve for A, the acceleration. So go ahead and do that. Try to find A. You're going to drop something, have someone time how long it takes from the time you dropped it to hit the ground. You put the height in for delta x, you put 0 in for VI, and you put the time that it takes to hit the ground in for T. Okay, that will leave you only A that you have to solve for, and then you solve for A. Okay, so once you find a value for A, then you're going to experiment a little further, and you're going to try to drop things from even higher height and see if the value for A changes. Okay, so go ahead and design your experiment, and good luck and have fun.